Hi everyone, my name is Iryna and I'm a Ruby developer. And when I got asked to speak at this conference, I asked the organizers if there was a particular topic that they wanted me to talk about today. And they said, you know, something practical, something that the people can get back to work the next day and put to work immediately. And the problem was that I wanted to talk about algorithmic complexity. And these sometimes quite abstract things and theoretical things. But the organizers, being the jolly people that they are, they said, fine. And so here we are, right after lunch, when most of you probably just want to take a short nap. At least yesterday, that's what I wanted to do after the lunch break. But we will talk about algorithmic complexity, and let's see how we do. And just a disclaimer, I'm not an expert on these things, by no means, but I used to do competition programming back in the day, and this framework of thinking about problems and efficiency of algorithms was just something very useful back in the day. And you don't have to be a competition programmer or compete in some sort of competitions in order to take advantage of this tool. The way I think about it is it's just another tool in your toolbox. It's just another way to think about problems. Similar to how maybe some of you at some point in their career ventured outside of object-oriented programming and maybe went and learned a functional language. And when you came back, you found that that made you a better programmer, that it just expanded your toolbox, it made you think about the problems in a different way. So that's how I think about this big O notation and assessing the algorithms. And for some of you in the audience, for some of you in the audience, this will not be a novel concept. Maybe for some, this will be. But it's just a refresher. It's a basic talk. We will cover the theory and then a few practical examples. So let's dive in. So, before we talk about algorithmic complexity, let's briefly mention what an algorithm is, even though all of you are probably aware. It's just a series of steps to solve a particular problem. And we as programmers, we write a bunch of these every day, so nothing new here. So let's just take an example problem. Imagine we have an arithmetic expression, that's an example, and we have to decide if the brackets in that expression are balanced. And by balanced, we mean, is there a matching closing bracket for each opening bracket? And if there are any brackets in the expression at all, is the first one an opening bracket? And if that's so, we assume that the expression is balanced. So we need to come up with an algorithm to solve this problem. And there's a bunch of ways to go about this. So maybe the first algorithm that you come up with could be described like this, and I don't imagine that you can read the slide, so I'll just explain what the algorithm could look like. You could say, well, let's begin at the beginning of our string and go character by character until we encounter the first closing bracket. And when we found the first closing bracket, let's now trace back and find the first opening bracket that's closest to that closing bracket. And if we find one, we just delete them from the string entirely. And we repeat this process over and over again until there's no more closing brackets left. And then we check if there's any remaining opening brackets in the string. If there's any that remain, it's an unbalanced string. If there's no more brackets that remain, then we assume that it's balanced. So it's sort of this algorithm that goes forward and backward and forward and backward and deletes some characters from the string. And it's not the most elegant solution, so maybe you spend a little bit more time and you sit down and you come up with a different algorithm. And let's say you decide that you create a variable, sort of a counter variable, let's call it balance. And you go through the string just once. And if you encounter an opening bracket, you add a number 1 to that counter variable. And if you encounter a closing bracket, you subtract 1 from that counter variable. And if at any point doing this operation, you go below 0, so you go into negative numbers, that's it. We stop. The string is unbalanced. It means that we have encountered a closing bracket that doesn't have a matching opening bracket. And if we have reached the end of the string, never going below 0, we just check what our counter variable is set to at the end. If it's exactly 0, we assume the string is balanced. So the details don't matter much, but we have two algorithms, and say we wanted to decide which is better. And this is quite an abstract question. I mean, what are we optimizing for? Are we optimizing for the speed of execution? Are we optimizing for memory consumption? Maybe we optimize for a speed of development or developers' happiness. We don't know. But let's say we optimize for the speed of the execution of the algorithm. Even when we niche down our constraints in our question to just the speed of the algorithm, it's still a tough question to answer. I mean, how do we measure the two algorithms? Which machine do we use to run them? Which compiler? Which operating system? Which amount of data do we feed to that algorithm to effectively measure the complexity of the algorithm? And so it's a bunch of questions. It's a fuzzy question to answer, and programmers needed a way to compare one algorithm to another in a sort of an abstract way, without being tied to a specific machine, to a specific running time. But before we answer that question, let's take a step backward and ask ourselves a more fundamental question, and that's, does it even matter? I mean, aren't computers like really fast? Can't they do billions of operations per second? Why do we even care about the complexity of algorithms and how long it takes to run something? And even if computers aren't that fast, we have the Moore's law that says that the number of transistors in a dense integrated circle doubles about every 2 years, which roughly means that every 2 years, we get twice more computing capacity that we have right now for the same money. So if you have a computer that's barely able to solve problem A, chances are that in 2 years, the same money will buy you a computer that will be able to solve twice the problem A. So the answer is yes, computers are very fast. And yes, we still need to care about complexity. There exist some real-world problems that we have the algorithms to solve, but oftentimes, given a sufficiently large amount of input fed to that algorithm, the amount of time it takes to run the algorithm is just not practical for many purposes. An example of such algorithm is a chess playing engine. And we do have great chess playing engines that already are beating human players, but most of them use some sort of heuristic still to decide which move to make. It turns out that the space of all possible combinations on a chessboard is so large that for all practical purposes, we cannot write an algorithm that, given a position on a chessboard, just predicts all possible future moves by a computer and by a human that it's playing against, and give an answer as to which move is the best in any sort of meaningful amount of time. There exists algorithms like this in DNA sequencing, and even the old traveling salesman problem, which many of you have probably heard about, which says that giving a list of cities and distances between those cities, which is the shortest path from one city that travels across every other city exactly once and ends up at the original city. So we're trying to find that shortest path, and turns out that a brute force solution takes factorial time to compute, and oftentimes when there's a large list of cities, we can't apply that brute force algorithm. So, but just to illustrate this, I want to talk about the old tale of the wheat and the chessboards. And many of you, by a show of hands, how many of you have heard of that tale? About half of you. Yeah. So, so the story is said to be set in India, and the inventor of the chess game comes to an emperor, and yes. Somebody just remembered the story. Great. So the story is set in India, and the inventor of the chess game comes to an emperor and shows him the game. And the emperor is so impressed with the chess game that he says, "Name your reward. Anything you want, I will grant it to you." And the inventor of the game says, "Well, my ask is very humble. All I want is that we take a chessboard, and on the first square of the chessboard, you put 1 grain of wheat or rice. There are variants to that story, but let's go with wheat. So you please put 1 grain of wheat on the first square of the chessboard, and then on the second one you double that amount, so you put 2, and on the third one you double that 2, and so it becomes 4, and we go like that until we reach the end of the chessboard to the 64th square, and then I'll gather all my wheat and I will be on my way." And the emperor laughed and said, "You are a silly man. You could have asked me for anything, and that's all you asked me for a couple grains of wheat." But then they begin to count. So let's do that as well. So we get through the first row and we double the numbers, and by the end of the first row, we are at the number 128. And this probably doesn't come as a surprise. And furthermore, we developers are used to think in terms of exponents of number 2, so we count many things that way. So all these numbers are strange and familiar. 128 doesn't seem that large. All is good. We fast forward another row, and we are at 32,768. And still, to some of you, this probably doesn't come as a surprise. But fast forward 2 more rows, and bam, we're in the 2 billions. That escalated quickly. And anyone wants to venture a guess as to which number we will end up at the end of the chessboard? Yes. Does anyone know how to pronounce that number? I don't know how to pronounce that number. It's ridiculously large. I know that when we put it 2 to the power of 64, it seems simple. But when we write it down in a decimal notation, it suddenly dawns on us just how large this number is. We as humans in our everyday lives are not equipped to handle these numbers, to imagine them, to estimate them, to compare them. We could just as well written, wow, a lot here. And this just shows how such a simple function as doubling numbers very quickly gets out of hand, and the numbers become ridiculous. Another example is the falling domino theory. And you know how you can lie in a bunch of dominoes and you knock down the first one and it knocks all the rest, given that you have positioned them properly? Well, in the 1983 study, a physician, Lauren Whitehead, demonstrated that a falling domino can not only knock down the domino of the same size as its own, it can actually knock down the domino that's up to 50% larger than itself. So an obvious experiment was then, well, if we line up the dominoes like that, such that each next domino is 50% larger than the previous one, how quickly and to which heights of the dominoes do we get? Turns out that by the time you get to the 23rd domino, its height is going to be higher than the Eiffel Tower. And when we get to the 57th domino, its height is going to be almost the length from the Earth to the Moon. And this just shows that certain numbers and certain rules of doubling numbers, if left unattended, will get ridiculously large. So to summarize, yes, computers are fast, but still, some numbers are just too large. And so complexity matters, and it matters not just only in those esoteric algorithms and sorting algorithms and searching algorithms that are often provided for you as a developer as a part of a framework or a library. It also matters in your everyday tasks, and I will cover more about that in the second part of the talk. So given that complexity matters, and given that programmers needed a language to talk about the complexity of algorithms, what came is the big O notation, just a way for developers to compare algorithms. And even if you have not really studied this, because I know that many programmers have not studied computer science in university. They stumble onto it as a second career, for example. But you might have seen these around. So for example, this is just a tutorial, a programming tutorial that I came across, and I've highlighted a few sentences from it. So it says like, this again is very slow, it's big O modulo x to the power of n, we can use dynamic programming to speed things up, and then they do the magic, and they say this now takes big O n multiplied by x, I think, and a big O n of space. So this is something that's encountered very frequently. Or if you checked and studied sorting algorithms and data structures, you might have come across this ridiculous, humongous chart that lists complexities of every operation in a sorting algorithm and in a data structure. So it's everywhere. But when you go to any sort of formal definition, let's say in a Wikipedia or another resource, it involves a lot of mathematics. It sometimes can be a bit confusing. It makes you pause and think if you really want to get into it. The official formal mathematical notation for the big O notation is this, and it doesn't look very friendly. So let's take it apart bit by bit. So what this really means is that f of x is considered to have an order of growth that is g of x, if and only if, starting from some point on x-axis, function f of x is always smaller than g of x. And I put it with a caveat here, because there's this k term, a constant term k that we're not taking into account. We are simplifying things a bit. We'll get to it a bit later. And to better visualize this, it's useful to plot the functions on a coordinate system. And just a primer to how we plot functions, in case somebody forgot. So we take a bunch of random x values, we put them on the horizontal axis, we calculate the value of f of x, we put them on the vertical axis, we trace these dots together, they come together in these 3 dots, and we put a line or a curve through these dots, and we end up with a graph of a function. So that scary mathematical formula that we just looked at, if visually graphed onto a coordinate system, this is what it looks like. And roughly, the intuition that could be used for the big O notation is that function f of x is bounded by g of x, meaning that it doesn't go higher than g of x. Well, technically, g of x multiplied by k, but let's just simplify it. It doesn't go higher than g of x. And if it doesn't go higher, then we say that f of x is big O g of x, or has the complexity of g of x, or has an order of growth of g of x. And you may say, wait, what do you mean doesn't go higher? It does go higher over here. Well, remember in our formula we said that starting from some point on x-axis, so there exists an x naught, some point on x-axis, x naught, after which, no matter how far we go into infinity, that function is guaranteed to never go higher. But what happens in the middle and the beginning, we don't really care about. And that's really all there is to the big O notation. And this is why, even though it's a notion that's used widely in mathematics, it's perfect for comparing the complexity of algorithms. Remember how we said that computers are really fast, and we don't care what happens on a very small input of data, because oftentimes, no matter how inefficient your algorithm, if you need to sort an array of 5 integers, you will probably get by with any sorting algorithm, with a bubble sort. So we don't care what happens in the sort of like small small inputs. We only care what happens when we go towards the infinity. So this very lenient, very loose definition of big O notation comes really handy when we talk about this question of how to compare algorithms. And the questions that we are asking are these. In terms of time complexity, how quickly does the runtime of an algorithm grow compared to the size of the input, as the size of the input increases? Meaning, if we increase the number of elements in an array and we want to sort it, if we increase it by 2 times, if we double the amount of elements in an array, by how many times will the runtime of an algorithm grow? And the same notion can be applied to the space complexity, meaning how much additional memory does the algorithm allocate as we increase the input. That's really all we care about. We don't care about the precise milliseconds that the algorithm takes to run. We don't care what happens when the numbers are small. We only care about how quick the complexity rises as we approach infinity. And here's why. We assume, the intuition to, at least to use about it, is that we assume that we do have lots of computing capacity on planet Earth. And if there's an algorithm that we can barely solve with the entire computing capacity of planet Earth, but we need to solve a slightly bigger problem. If the complexity rises slowly enough, the Moore law will kick in and catch up, and we will still be able to manage to keep solving this problem in a way. So it's the same visualization, the same way to visualize it, but I've mapped it. I've stepped away from abstract functions and mapped it onto our complexity domain. Our horizontal axis now becomes the size of the problem, and the vertical axis becomes the abstract amount of operations we need to make. And so this big O notation just allows the developers to have a small vocabulary to talk about complexities. And by small vocabulary, what I mean is that notice how this red line is all curvy and weird, and this black line, the G of n, is smooth and nice and pleasant looking. And that's the core of the complexity analysis, is that your algorithm may very well have a runtime that behaves like this red line, that's quirky and hard to analyze. But as long as it's bounded by this nice and smooth line of G of n, we say it's the same as if it has the complexity of G of n, and then we have just a few, a handful, not really a handful, maybe between 10 to 20 most common complexities that most developers use. It's a constant, logarithmic, log linear, linear, quadratic, exponential, factorial, etc. And we say that why this is so useful is that when mathematicians and when developers hear, for example, a quadratic function, immediately in their head, they have a picture of that, how that function looks and how quickly it grows. So if you were to explain to them that you have this algorithm that behaves like f of n, it may be very difficult to explain. But when you say it's bounded by a logarithmic function, everybody knows what a logarithmic function looks like. So it's very easy to communicate. So it's just a vocabulary. We are narrowing their vocabulary to most used complexity functions. So let's have a look at those, what those are. Constant complexity is written as big O1, and it's an algorithm that no matter how many data you put and you feed into it, always takes a constant amount of operations to compute. An example of such algorithm is, for example, capitalizing a string. No matter how long a string you feed into it, it roughly takes a few operations to take the first letter, to make it uppercase, and to return it from a function. And a mistake I often hear in discussions and in interviews is that people want to take an algorithm, let's say capitalization of the string, and they say, well, one operation is finding the first character, another one is getting its ASCII code, and then another one is looking up the ASCII code for the uppercase character. So they count, let's say, 5 operations that are needed to capitalize the string, and they want to say that the complexity is big O5. That's usually a mistake. The property of big O notation is that we drop the constants. So if you want to say that the complexity is big O5, it's the same as big O5 multiplied by 1. 5 can be extracted out of that equation, and if it can be extracted out, it can be dropped completely. We always say that any constant operation is big O1. And again, this rule can fall flat on your ears, and you may forget it tomorrow. So I'd like to provide a useful intuition to think about this notion that we can just simply drop constants. How can it be that we can drop constants? Well, again, we imagine that if we have a computer that is able to perform one operation, one basic operation of your algorithm, and not able to perform any more, it doesn't matter, we don't have the money or like the capacity, there are no more computers left on planet Earth that we can scramble together to compute the whole 5 operations of this algorithm. We think that, okay, then we wait another 2 years, another 4 years, Moore's law will kick in, we'll have more computing capacity, we'll still be able to solve this problem in a meaningful amount of time, in a practical, manageable amount of time. So that's why we don't care about the constants. We just drop them, we say it's big O1. Another popular complexity is the linear complexity, and it's when an algorithm takes roughly as many operations as the amount of data you feed into the function. For example, it's finding an element in an unsorted array. Because it's unsorted, you have no choice but go one by one until you encounter the element that you're looking for. So in a best-case scenario, you got lucky, it's the first character, you only had to do one comparison. In a worst-case scenario, it's the last character, and you had to do n comparisons to find the element that you were looking for. And generally, when we talk about the big O notation, we talk about the worst-case scenario. So we consider these algorithms to be linear, meaning it's proportional to the size of the input. And of course, there are certain algorithms where, in an average case, they perform quadratically, for example, but in a worst-case scenario, they become exponential. But the worst-case scenario comes so rarely that the mathematicians go into the trouble of separating a worst-case scenario from an average-case scenario. But generally, we only care about the worst-case scenario. So searching in an unsorted array is one of those, is a linear type algorithm. And I'll skip this slide because we talked about the constants. Then the quadratic complexity comes in anytime there's a nested loop, or, for example, a bubble sort, a naive implementation of a sorting algorithm called a bubble sort, where you go through each element in an array and compare it to every other element, and you switch places if you found that the elements are out of order. And for example, if you had an array of 5 elements, if you compare each element to every other element, it in a worst case scenario, it takes you 25 comparisons. But then if you double the size of that array, so you go from 5 to 10, suddenly you have to do 100 comparisons, because 10 to the power of 2 is 100. So we doubled the input, but we almost quadrupled the amount of operations we have to make. So it's not very nice of quadratic complexity algorithms to do this. And oftentimes, quadratic complexity will get you into trouble if the amount, each operation takes a lot of time. Even worse than quadratic complexity is exponential complexity, and that's what we saw with a chessboard problem, was an exponential rise to the numbers. And anytime you write an algorithm that behaves exponentially, you really have to think about the impacts of that decision. And my favorite type of complexity is the logarithmic complexity. The logarithmic function is an inverse of an exponential function, and so equally to how the exponential function rises ridiculously fast, as we saw with the chessboard problem, in the same way, the logarithmic complexity is ridiculously contained, no matter how large an input we feed into it. I believe the logarithmic log base 2 of a trillion is 39 and something, so roughly 40. And what this means is that if you had 1 trillion elements in your database, and they happen to be in a sorted order, because for some reason you inserted them and you maintain that order, if you're looking for one specific element in 1 trillion other elements, because they're sorted, and you can take advantage of a binary search algorithm, which means you divide things in half, you look straight in the middle, you try to decide if the element you're looking for is to the right or to the left of that middle, you discard a half of the data, and you repeat that over and over again. So you're roughly just halving the data over and over again. And turns out that to get from 1 trillion to 1, it only takes roughly 40 comparisons. So you can find an element in an array of sorted trillion elements in just 40 comparisons, compared to how with a linear search, well, in a best case scenario, of course, you do 1 comparison, but in a worst case scenario, you do 1 trillion comparisons, which can be really, really expensive. So here's a comparison table of some of the complexities, not all of them, just a few. But they're color-coded, and as you see that we try to get in, with our solutions, we try to get into a constant or a logarithmic complexity. And then sometimes the linear complexity is okay. Quadratic tends to be a little bit problematic, but as soon as we venture outside the quadratic complexity and go into exponential and factorial, that's when we are really in trouble. So if there's just one thing you remember from this entire talk, is try to get your solutions down to a constant, a linear, or logarithmic complexity, which means these 4 things. And I added the log linear, which is n times log n. It's still manageable. And the question could be, well, how do I do this? Well, think whether you can divide and conquer. Think whether you can take advantage of dividing your data in half, and then in half, and in half, and in half again. This works miracles, usually. Think whether you can have your elements in sorted order. Would this help? Think of whether you can choose a data structure that better reflects your algorithm. Maybe you don't need an array. Maybe you need a balanced tree. Maybe you need a red-black tree. And it helps you read up on those data structures. But oftentimes, what I found, what helps tremendously, is just keeping this entire framework in mind. Just asking yourself, what will happen to my solution as numbers get ridiculously large? And believe me, they will. I want to jump to some practical examples quickly. And both of these are real-world examples. And the first one happened on the project that I worked in. And we hired a very seasoned developer to implement a one-time password system. I'm sorry, I don't think these are very clear. There's some things going on with the projector, but let's just try to get through it. So the task was to implement a one-time password system. You know how you log in into the system, and in addition to supplying a username and a password, you're also required to enter a PIN code that's usually delivered to your mobile device, and it's just sometimes 4 digits. And so he had to build a very simple API-powered solution where in one case, there's a username that comes in as input. The system issues a PIN code, a 4-digit PIN code. That PIN code is delivered to the customer's phone. And then when the customer enters the PIN code into the form on the website, we again contact the PIN system and say, this customer entered this PIN code. Is it valid? Is it not valid? Does it match what you issued in step 1? So extremely simple. But for some reason, the developer decided that he wanted to make the PIN codes unique, even though there was no such requirement. These don't have to be unique, as long as they're random. But he wanted to make them unique, so this is a rough algorithm that he came up with. He generated the random PIN code. He checked in the database if it already exists. And if it already exists, he just kept generating random PIN codes again until he found one that wasn't already issued to a customer previously. And if some of you are laughing, and rightly so, and very good for you, you have guessed what happens when we have used up most of the range of 4-digit PIN codes, which is not large at all. 10 to the power of 4 is only 10,000. So the system, we didn't have code review. The system only generated 10,000 PIN codes until it could no longer generate a PIN code, because it would generate a random PIN code, trigger the database, it was already there, it would generate another one. And as we are here, as long as we have just a few more left, still bearable, even though we are making n or sometimes a few times the number of used pins in the database, depending on how lucky you are. But that was a terrible decision. And if we look at this algorithm, we could say that it has a complexity of an infinity, because at some point it just simply breaks. But of course, you could say that's just a buggy algorithm. It's just a dumb decision. The person should be fired, and that's the end of the story. But just keep this example in mind as we go into the next example. So imagine a boss comes to you in your company. He says, you know what, we are going to build a new product, and it's going to be a URL shortener. It's very simple. It's your responsibility to build it. So this is how it looks like. A customer comes, and they supply a long URL, and you have to give them a short URL that then redirects to that long URL. So similar to how Bitly operates. And when you hear this task, you're probably in your mind, you're already thinking in terms of the database and just a few controller actions, very simple. But then the boss says, but I have a few additional constraints. First of all, I want the hash part of the URL to be really small. I want it to be only 5-digit and characters, because people sometimes will want to remember these URLs, and as long as they're short, it's user-friendly. And then he says, and because I want to keep them so small, I want you to use up the entire possible range of combination of 5-digit hashes before you move on to a 6-digit hash. Because of course, if you exhaust the entire range, you have to make the hashes longer. But before we absolutely have to do this, I want to issue every possible combination. And there's some prohibited characters like 1 and L and O and 0, because they're easily confused. And then another thing that he wants is he wants to make these hashes random looking. So he doesn't want them to be like all A's and then AAAAB, AAAAC. And the reason for that is he wants to sell the company in the future. And he says that, well, if we go alphabetically like this, when the potential buyer comes, they can very easily deduce how many URLs in general we have issued so far. And if that's a small number, they may not want to pay a big price for our company, so we want to obscure that information. So no cryptographic, no security requirements, but just please make them sort of random looking. And even though this requirement doesn't seem like a deal breaker, when you get into the implementation, let's have a look at how things would look if we didn't have this random looking URL requirement. Well, we would issue, the first customer comes and we give them the URL that's the first in the alphabetical order, which is all A's, and then the next customer comes, we give them the second one, and let's say we have issued 5 URLs, and now the 6th customer comes. Well, what do? We simply look at the last URL that we issued, and we know how to come up with the next one in an alphabetic order. We know that we just take this last character, that's E, and we know what comes after E in an alphabet, A, B, C, D, E, F. So then we leave this part the same, it's 4 A's, and we replace the E with an F, and that is it, and the customer is on its way. But because we have to generate these sort of random looking numbers, we start to think how we can do this. And you could come up with this naive solution, generate a random, sounds familiar, generate a random hash of 5 characters, check if it exists already in the database, and if it exists, generate a random one again, and keep going like so until we find a random hash that doesn't exist in a database yet. And we could add all sort of preventive checks saying that, but if we have exhausted our range, then go on to to a length of 6. But you will still get to a point, oh, I think I missed a slide. You will still get to a point where you have used not all, but most of the space of your combinations. So only a tiny fraction of available URLs remains. And when you try this algorithm of randomly generating these sequences, you will end up triggering database time and time and time and time again. It's becoming very resource intensive. So another try at this problem may come when you remember that there's this awesome thing in mathematics called a hashing function. So you think, what if I just, each URL is assigned a unique numerical ID, it starts with 1, and then I take that number and I feed it through some sort of hashing algorithm. I know that these hashing algorithms produce this weird long combination of letters. I don't need that much, I'll just trim them down to 5. And of course, there will be some prohibited characters. I'll just replace them or remove them, and that's it. And the problem is that even though hashing functions are great and they have all of these incredible mathematical properties, such as being almost collision-free, and the problem is that this is very close to your randomized solution. As soon as you begin chopping them down and replacing characters, you lose all of those mathematical properties. And this is just the same solution as just generating random numbers, and you still have to trigger the database to check if these generated sequences exist. So you sit down and another day passes and you think, okay, fine. If I absolutely must come up with these randomized strings, and if I absolutely need to make sure that I issue every single one in the range of 5 of the hashes that are 5 digits or 5 characters long, then to hell with it. I generate all possible combinations, and then I shuffle that array, and I store it in the database, and then whenever a customer comes, I'll just give them the first URL, and then the next customer comes, and I give them the second URL, and so on. And you think that, okay, so there's 26 letters in an English alphabet, plus the 10 digits, minus the 4 prohibited characters, that's 32, to the power of 5, that's 33 million and something, and you're thinking, I have seen databases that are that large, not a big deal. Maybe we can afford a server with a database that large, and you're thinking, that may be my solution. I just generate 33 million of these possible combinations. I put them all into the database, and voila. But you might pause and think, what happens when you have coded all of this up and you've started issuing these URLs, and then your manager comes to you and he says, you know what, I've really thought about it, and I don't want to do the 5, I don't want to do the URLs that are 5 characters in length. Let's do 15. I think the 15 is really the right number here. And suddenly, 32 to the power of 15 is this ridiculous number, and it's no longer practical to store them all in the database. And you might say, whoa, 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 whoa. This changes the entire dynamic. Now that the space is so large, we could actually go back with our randomized solution, because now the chance for a collision is so small that it's really we can neglect it. But do you really want to change your entire code just because one constraint changed? Do you really want? Isn't there a more elegant solution that we can apply that's both effective and resilient to changes like these? And if you think about it, when we think of the problem in a non-randomized way, the reason it's so straightforward to implement is that we as humans, we know how alphabet works and more so, we have all seen a mechanical rotating dial of sorts, and this is a mechanical dial that has three dials, and each has a feed of 9 digits. And we know that we first rotate the outermost dial through all the numbers, and when that's over, we just rotate the middle one by one, and then repeat the whole thing. And that's how we get through all possible combinations in that alphabet. So this is sort of what it looks like when we're generating these alphabetically. We have 5 rotating dials. Each has a feed of alphabetically ordered characters that are allowed in our URL generation. And what if we took these feeds and we shuffled them? So instead of having these alphabetically, we just shuffle them and do the same thing. And so now we store them somewhere in the database, so it's done once. And now when the customer comes, we generate these in much the same way as we would with the alphabetical solution. But suppose we had 5 customers, and now the 6th customer comes. So instead of replacing 8 with a 9, which would come alphabetically, we replace 8 with whatever number comes after 8 in one of these pre-shuffled arrays. And now we no longer have to store 33 million of records in the database. We don't have to hope that we're lucky and we are generating random numbers and we do not run into collisions. And if we think about the complexity of this algorithm, so the time complexity to issue the next URL is constant. And then the space complexity is linear, and you don't really get any lower than linear in terms of space complexity, meaning that however many customers we have had, that's how many records we have in the database, because you have to remember which URLs redirect to which other URLs. And so this just demonstrates how just thinking about the complexity, just asking yourself a question, what happens when we get to sufficiently large numbers, have triggered us to come up with this really creative algorithm. And that's really all that I have to say. I love this topic, so if you have any questions or if you just want to talk afterwards and talk to me, I'll be happy to do so. And thank you for sticking with me after lunch. I know it's difficult.
Thank you.